back from break. So let's look at the rest of chapter 19. I think you've already found there's a lot of stuff in chapter 19. We have some more stuff left that we want to make sure that we get a look at. So let's do this. We're at the point now where we're entering they introduced the first law of thermodynamics, which is energy conservation. It says the internal energy of a sample of some atoms or molecules depends on how much heat is transferring in and how much work is leaving. The minus sign here is probably unfortunate, but that's the way it's been defined. So again, we're not looking at internal energy itself, but we're looking at changes in internal energy. So I've already got a certain amount of internal energy. We add some heat, that contributes to the internal energy. Or I transfer out some work, that will drop the internal energy. So it's the law of conservation of energy at the molecular level. So let's try this. It shouldn't be that difficult, right? It's like, Q minus W. So what does this look like? Now in the example it says that we have 25 joules of heat added to a system. Now that makes sense. Clearly added to a system means 2,500 joules are being transferred in. We're placing the sample in a higher temperature environment, and as a result, Q is going into our sample. Now, I have always had issues with the way that we describe work, and I realized when I went back through my notes, I think I got this backwards. So you guys are going to have to tell me. It says 1,800 joules of work is done on the system, and I think that means the work's coming in. So they have this, I don't care for the, I guess it's not the verbs, it's the prepositions. Work done on the system means it's coming in. Work done by the system means it's leaving. And I didn't read carefully. And so I got this backwards, but let that be a lesson. We'll have this be a learning experience. Read carefully. I am usually going to write this differently because, let's go ahead and look at the problem. So here's the way I'm going to think about this. I got a container. It's got a variable volume. Now it needs to have a variable volume because work means that the gas is either expanding and transferring energy out, or it's being compressed and energy is being transferred in. Those are the two options: expansion or compression or contraction. So here is a sample of what's happening. Now, inside we already have internal energy. Our question is, how will that internal energy vary? Is it going to go up or is it going to go down? And as far as heat could be coming in or heat could be leaving. And I draw these, I draw these diagrams like this. Again, I don't care for formulas with plus or minus signs in them as much as looking at the diagram and keeping track of which direction that sign should be in. So Q being added to the system means it's coming in, and that's going to be an additional 2,500 joules. Now, I misread the problem, and I assumed that the work was leaving the system, that there was an expansion taking place, but instead there was a compression taking place. Now that I'm going back and reading it. So anyway, if there was an expansion, then 1,800 joules would be leaving. If there's a compression, 1,800 joules are coming in. So now the sign here, again, I don't want to think of it this way. I want to think of it as 2,500 joules are coming in and 1,800 joules are leaving. So I'm going to put a minus sign in there by hand to say that it's leaving. And as a result, the net effect on the internal energy is that the molecules now have 700 additional joules of energy. That's the delta E internal. Now, I think the way the problem was intended is energy was coming in both from heat and from work. Q and W being added. And again, I'm kind of ignoring this formula and just saying, from the diagram, if there's a compression taking place, that needs to be a plus sign. So that would be 2,500 joules plus 1,800, and that's going to add up to 4,300, I think, joules. I think that was the intention of the problem. But you know, let this be, again, I'm going to treat this as a good example to think in terms of, did the volume go up or did the volume go down? If the volume went up, that was an expansion, energy is leaving. If the volume compressed, that's a compression, energy is going in. That's the convention. So I hope in easy to understand vocabulary. Let's look at a couple of processes and ask how much work, how much energy is being transferred due to work, due to an expansion or a compression, in the case where the process is constant pressure, which we call isobaric. So constant pressure would say, well, it's isobaric. The way the work integration is done, the work on a PV diagram, the work is the area under the curve. So I can look at the area under the curve and say that the amount of energy being transferred in going from A to B indicates the gas is expanding out into the environment, and that says that energy is leaving the gas. So, or whatever the sample is. So going from A to B, the energy is leaving our system, and the amount of energy leaving is P delta V. Now that's isobaric. What happens if it's isovolumetric? What if the volume is fixed? Well, if the volume is fixed, there's no W. Work does not happen. So that's one of those, you know, there was that table outlining the different processes, and bottom line is if the volume is not changing, work is equal to zero. There is no area under that curve. So, so a couple of good diagrams. Now, this approach of area under the curve works for any process, not just isobaric and isovolumetric. All right, here it is. This is what I was waiting for. Here is my container. Here is the sample. In this case, it's an ideal gas. It does not have to be an ideal gas. But with gases, we certainly can have a lot of compression or a lot of expansion very easily taking place. So we'll say the sample is an ideal gas, and then the piston moves back and forth, and as it does, the volume changes, and as a result, the pressure will be changing too. Now, for an isothermal process, one in which the temperature is not changing, that says that this sample easily transfers energy. So all I have to do is put this in a fixed temperature environment, and then if I compress, well, some of that energy that comes in leaves and the gas still maintains the same temperature. If I expand, some of the energy is lost in the sample, but thermal energy can transfer in. So if I put the container, if I make the container so it's very easy for heat to transfer in or out, it's got very good thermal conduction properties, that can allow that gas to maintain the same temperature. Now on a PV diagram, those isotherms are hyperbolas. So I'll have a series of hyperbolas. Starting in here, the temperatures are lower. As I move out to further and further to more and more hyperbolas, each additional it's at a higher temperature. So more and more temperature as we move out. Now that's really handy because now on a PV diagram, I can also indicate what's happening in terms of temperature, higher temperatures or lower temperatures. Okay, there's a fourth process we want to consider. So let's see, what have we talked about? Constant volume, constant pressure, constant temperature, and now the fourth process. Now, of course, the processes are more general than this, but we're looking at kind of four that have a certain set of properties to them, and we can use combinations of those four processes to represent or approximate different processes that might happen in a real situation. So this is our isothermal process that maintains a constant temperature. What if this happened? What if there was an expansion from from A to B there is an expansion and it's isothermal, but what if the expansion happened, looking at our container here, what if an expansion happened but the container is insulated? What if it doesn't conduct heat? Well then there's no way to get Q transferred in and the temperature will drop. And that's an adiabat. So adiabats correspond to no heat transfer. And we can make sure that the heat transfer is essentially zero, either by having the process happen quickly. If a process happens quickly, there's not as much time for Q to transfer. Or the other possibility for an adiabat is that the container is really well insulated. That can also lead to an adiabatic process. And notice if it's an expansion that's taking place, that means that the energy transfers out, it's not replaced with an adiabat, and as a result we end up at a lower temperature. All right, here is the general formula for work. In general, energy transfers through work are a force times a displacement. But now that we're working in terms of gases, we can switch, and instead of force times displacement, we can work in terms of pressure times volume changes. So the pressure times dV represents a little bit of work, and that's our general formula. We can integrate that formula to calculate the work. So let's do that. Let's practice. For an isothermal process, one in which the temperature stays fixed, we're going to represent that as this process right here from A to B. A to B is in the direction of the expansion, isothermally. From B back to A would be an isothermal compression. Here is the work formula. We integrate PdV from a starting volume to a final volume. Now, I can't really carry out that variable, or that integration, because P is not constant. P is a variable, and P is not V. I need to get P in terms of V. Now there's a way to do that. I can get P in terms of V by using the ideal gas law. So I'm going to take this expression, nRT over V, and I'm going to substitute that in. Now n is a constant. You know, the sample size remains fixed during these processes. R is a constant. That's just the gas constant that applies to all phases. And then T, because it's isothermal, T is also a constant. So that comes out the integral. The only thing that gets stuck inside the integral is V. Well, that's not a problem because that's our variable of integration. So dV over V integrated gives us nRT ln of V B over VA. And there you go. That's a formula derived that will tell us the amount of work done in going from A to B. Now, the way the formula works, the way it's defined is P dV. So if the expansion is happening and we're going to larger volumes, this is going to turn out to be a positive number. But again, I can use my diagrams, the little sample diagrams, and indicate which direction the energy is transferring. So for an isothermal process for an ideal gas, that's our formula for work. And that's going to be leaving the system if there's an expansion, and that much work will be going back into the system if it's a compression. All right, let's try, we looked at an isothermal expansion. What would happen if now we took a different path? Instead of going from A to B, what if we go from A to D? Where is C? What if we go from A to D first, and then from D to B? Will the amount of work be the same? And it won't. We can see from the PV diagram that different paths going from A to B will have different area under the curve. So visually, we can look at the PV diagram and say, if I go from A to D, that's no work at all. And the work that is leaving the system from D to B is not as large. I can see that the area under this curve is not as large as, I'm missing all this part. So the path makes a difference. If I'm calculating work or if I'm calculating heat, W or Q, different paths from A to B will lead to different values. Now what doesn't change is the internal energy. So the internal energy only depends on what the temperature is, and so there's a fixed temperature at A, there's a fixed definite temperature at B, and it doesn't matter how I get from A to B, by the time I've made the journey from point A on my diagram to point B, it's going to represent the same change in internal energy. So energies don't depend on the path, but Q and W, both of those do depend on the path that we take. So something to keep in mind. Now here's just a conceptual question. It's saying if I go from A to B along isothermal and expand, and I go from A to C along one of those adiabats that we introduced, how will the work how will the work compare? And again, I can visually see that since A to B keeps me on the same isotherm, but if I expand adiabatically, that brings me to a lower isotherm. And the area under the adiabatic expansion is less. So there's a smaller transfer of energy through work. The gas will lose more energy in the through work in the isothermal process, and it will lose less energy through work in the adiabatic. Okay, so that's how those are going to compare. The W going from A to B is going to be greater than the W going from A to C. And again, we can see that visually on the PV diagram. All right, here's a problem. It says that we've got this process isothermal from A to B, but then we're going to go back from B to D, and then from D back to A. So they're saying that they're really starting at point B on this one. So they're starting at point B, which they say is at a constant a pressure of 2 atmospheres. So we're going to go from B to D. That's the 2 atmospheres constant, dropping from 10 liters down to 2. And it says during this process, what we're going to find is that Q is leaving the system and the temperature drops. Well, we can visualize where those isotherms are, and definitely the temperature is dropping for this process. Then what we're going to do in a second step is we're going to start adding Q back into the system, and the temperature will start coming up, the pressure will start coming up when we do that. Now from B to D, in addition to the heat that's leaving, work is being put back into the system because we're compressing the gas. From D to A, no work is done because there are no volume changes. So they want us to go in, and I think what we do is take the individual steps, calculate the Q's, calculate the W's, calculate the differences in internal energy. So here are those 2 processes, B to D, D to A. From B to D, it's an isotherm, and so what we can say is that the pressure at B, we're just doing units conversion here, pressure at B is 2 atmospheres, which converts into 202,600 pascals. So we're going to be doing joules calculations. Joules are standard units, and we're going to get those by taking pascals for pressure and cubic meters for the volume. So the 2 atmospheres and the 10 liters, when I do the units conversion, turn into 202,600 pascals, 0.010 cubic meters. Now the number of moles they tell us is 1, and that's always interesting when they tell us the sample size happens to be exactly 1 mole, but that's fine, we can work from that. So there's 1 mole, that tells us how many molecules are in there. Now the temperature at point B, we can actually get by using the ideal gas law and taking PV over NR. So that's going to work. So I'm putting in standard units, PV, VB, N, and R, and I'm getting a temperature of 244 Kelvin. So this is a low temperature process that we're running here. This is some cryogenic equipment of some sort that we're operating. That's a really low temperature. Now, what's going to happen is if the temperature at B is already 244 Kelvin, well, the temperature at D is going to be really low. I can see that from the PV diagram. And for calculating that, we can take the ideal gas law for point D and write that down. And then we can take the ideal gas law for point B and write that down. And then we can cross off all the things that are remaining constant. So this is the ratio technique. We've used this before. It can be a very powerful technique. And so the N's cancel, the R's cancel, the P's cancel, and I'm left with the ratio of volumes is proportional to the ratio of temperatures along that path. So I plug all the numbers in, and what I find is that the temperature has dropped by a factor of 5. So the temperature's gone all the way down to 49 Kelvin. This really is a low temperature, it's some low temperature equipment that we're looking at. Whatever this equipment is doing, it is maybe intentionally reaching really low temperatures. Okay, 49 Kelvin, that's, you know, at 49 Kelvin, it says it's an ideal gas, but by the time we hit 49 Kelvin, nitrogen's a solid, oxygen's a solid. What's still an ideal gas at 49 Kelvin? Maybe helium or neon, one of the inert gases, would still be in the gas phase at that really, really low temperature. All right, and then what we're going to do is we're going to go back up to the pressure at point A. We're going to get all these things calculated. We're going to get the P's and V's and T's determined at all 3 of the points. And then we can work from those numbers. So I did the ratio thing again. This time I compared point A with point B. Now the temperatures at A and B are the same. So the N's cancel out, the R's cancel out, the T's cancel out. And I can use that ratio method to find out that the pressure at point A is equal to 10 atmospheres. Now for right now, I think we're okay leaving that in atmospheres. We'll see if we need to get that converted also. Maybe we will. All right, so I went back. I wrote down the temperatures in kelvins. That looks good. I put the volumes in liters. Now, as needed, I'm going to have to convert those into cubic meters. And then the atmospheres I left, the pressures I left in atmospheres. And again, I'm going to have to convert those quite likely. Now, I drew my little diagrams here that I enjoy drawing. So for process B to D, we're compressing the gas, but at the same time, the internal energy is dropping. So it must be we're losing a lot of Q. And if we go in and use the formulas for a constant pressure process for work, that would be P delta V. Now this is at a pressure of 202,600 pascals, and the pressure is dropping, or the volume is decreasing. Now it comes out as a minus number, 1,620 joules, but remember, those 1,620 joules are going in because it's a compression. And that's why I have issues with these numbers. So again, I like to just use the absolute value and calculate, oh, it's 1,620 joules, and my diagram is showing, oh, the energy is going in because it's a compression. So the internal energy is going to get a boost from that compression. Now, when I go to D to A, that's isovolumetric, and that means W0. So W is, first of all, 1,620 joules transfer in, and then the next step, no energy goes in through work. So that's the contributions through the compression. Now, the internal energies, rather than jump ahead and try and use the Q's, I could do the internal energies. This is monatomic, so maybe it's helium or neon, something like that. And at least that's what I calculated for. So for the monatomic, 3/2 nR delta T. I put in the number of moles, I put in big R, and then I put in the temperature differences. So you can see, once we have filled in the temperatures table, once I filled in the temperature and the volume and the pressures in that table, I can just work from that table. And looking at the temperatures, I see that the temperature went down by 195 Kelvin on the first step. That's a drop of 2,430 joules in internal energy. Okay, and that minus sign there makes perfect sense to me. The energy has dropped down. Now from D to A, the temperature goes right back up by the same amount. Notice that A and B are on an isotherm. So if I go right back up by the same amount of temperature change, then I'm going to be putting, along that process, I'm going to be putting the same number of joules, 2,430 joules, right back in. Now, in the first case, there was both work and Q involved in transferring out the energy. Work was actually putting energy in, and that meant, when I do the calculations, the Q that was being lost was 4,050. Now on the second step, the work is 0, and that says that all of the energy that came back in came in through Q. Okay, so I can always do this. I can always calculate the W's. We have a set of formulas for those. I can always determine the delta E's because we have formulas of those in terms of temperatures. Once I have the delta E's and the W's determined, I can always calculate the Q's by adding those two effects together. So that's a good example. And here actually is a table. I kind of got ahead of myself on that. Here's a table with all of the things to remember. If it's isothermal, then delta T along the path is 0. Delta internal energy then has to be 0 too. Good to know. And Q then is equal to W, saying if Q is coming in, then W is leaving. Or if W is coming in, then Q is leaving. The isobaric process, P is constant. For a process where P is constant, I can calculate the Q as the delta internal energy plus the W. I have to add in the work effect. Now, for isovolumetric process, V is fixed, it's constant, and that means W is 0. Delta V is equal to 0, W is equal to 0. So all of the changes in internal energy have to be done purely by Q. And then finally for the adiabatic, Q is equal to 0, and that means that any changes in internal energy have to be due to work coming in or work leaving. So that's going to determine changes in internal energy. All right. Now for gases, the specific heat is going to depend on the particular process. If it's isobaric, the specific heat, the molar specific heat, CV and CP, are going to be different. So we need to develop a set of formulas for those. And again, I'm going to go back and use these diagrams. If it's constant volume, then all the energy coming in through heat equals the difference in internal energy, and differences in internal energy are 3/2 nRT. So for a monatomic gas, that would say CV, the molar specific heat at constant volume, is 3/2 R. Whereas for a diatomic gas, the molar specific heat at constant volume would be 5/2 R. Now let's switch over to constant pressure. If the pressure is constant, then as the Q comes in, the molecules are moving faster. But since the pressure is constant, the flexible container expands. And so energy gets lost due to the expansion. In the constant volume case, we didn't let the container expand. And that meant all the heat going in went to internal energy. So in the constant pressure case, we have to bring enough heat in to bring up the internal energy, but also we have to overcompensate because we're going to be losing energy due to expansion. Now we can show for a constant pressure process that work is P delta V, which, since we're at constant pressure, is the same thing as nR delta T. So we have to add that on. And that says, for a monatomic gas at constant pressure, I'm going to have 3/2 R plus an additional R. That's going to give me 5/2 R, because we've got to put more heat in to compensate for the lost energy through work. Now, if it's diatomic, then I start at 5/2 R, add on an additional R, and that brings us to 7/2. And I wrote the numbers down for what these are. If you look up different gases in tables, you'll find out that the monatomic gases, helium, neon, such, they match these numbers exactly, pretty much. The ideal gas approximations work really, really well for monatomic gases. For diatomic gases, they do okay. So, and there's a table in your text. For diatomic gases, they come within several percent. If we go up to polyatomic gases and try and estimate, it gets harder. But you can still see that there are definite patterns. Specific heats at constant pressure are always larger by 1 additional R. So here's a couple steps. So here's a compression of an ideal gas, and this is going to give us a chance to go in, check our formula for adiabats, check our formula for isotherms. So we're going to go from A to B first, and then from B to C. Now what they tell us is we start right at 1 cubic meter of volume and right at 100 kilopascals of pressure. I like those numbers. Those numbers sound pretty easy. By the time we get to C, the volume is at specifically 1/2 cubic meter, 0.500 cubic meters. So anything else we need to know? Oh, and 300 Kelvin. So they tell us at point A, we start out at 300 Kelvin. Let's just get the pressures and temperatures and volumes everywhere. We found out that that's pretty useful. So it's an ideal gas. It's monatomic. So it's either helium or neon or argon or krypton or xenon or something. And we're going to do an adiabatic compression from A to B, and then we're going to do an isothermal compression. Both of these are compressions. So in both steps, energy will be going into the system through work because there's a compression taking place. Now what I can do for this is I can write down what's given. These numbers are given. That's enough information. I have the starting pressure, volume, and temperature. I can calculate the number of moles, and the number of moles comes out very close to being 40 moles. It's a little more, 40.09. Now the CV and the CP for a monatomic gas, the molar specific heats, are 3/2 R and 5/2 R. Now what I've brought out here is the adiabat formula. Since the process from A to B is an adiabat, I have to bring out the adiabat formula. Now I didn't go through the derivation, but the book does a different formula with a different derivation. This formula includes pressures and volumes and temperatures. So I call it the super adiabat formula. This will solve everything. I'm going to make that claim that we can always work from this. Now, in this particular problem, what we are told is that pressure at A is 100 kilopascals and pressure at B is 200. Okay, there we go. Pressure goes from 100 to 200, and all we need is one set of ratios, and I can put that into the super adiabat formula right there. Pressure at B divided by pressure at A, it's a factor of 2. So that becomes a factor of 2. And then what I can do is use these funny powers. So the temperature ratio is to the 1 over R power. The volume ratio is to the 1 over CV. The pressure ratio is to the 1 over CP. This is CV. And then the volume ratio is flipped relative to the pressure and temperature ratios. So in an adiabat, P, V, and T, they all change. And the P and T are correlated. Pressure and temperature go up and down together along an adiabat, but the volume is inversely related. Okay, that said, what we know is this ratio. So I'm going to use that to go in and solve for this ratio and calculate the temperature. So if you remember from algebra, and the super adiabat formula is a great chance to go back and remember how to deal with powers. What we could do to solve for TB over TA is take each one of these expressions to the R power. If I take this to the R power, R over R becomes 1. This becomes R over CV, this becomes R over CP. So TB over TA is equal to PB over PA, R over CP. And remember, for our monatomic gas, the CP is 5/2 R. The R's cancel out, and what that says is it's this ratio of 2 to the 2/5 power. This gets flipped. And so the temperature will go up by a factor of 1, the absolute temperature will go up by a factor of 1.32. Now we started at 300 kelvins. When I multiply that by 1.32, I get 396. There it is. There is the temperature at point B. Now to get the volume at point B, I can go back to the super adiabat. This time I'm looking at volume ratios and pressure ratios. That is still a factor of 2, but this time I have to take it to the CV power to cancel this out. So this is going to become CV over CP. So there it is, VB over VA. Now the volume is inversely related. So this is VB over VA, but this is PA over PB now, to the CV over CP. Now PA over PB is a ratio of 1 to 2. So now I'm taking that 1/2 and I'm multiplying that by, or I'm taking it to the power of CV over CP. Well, CV over CP is 3/5. So this becomes 1/2 to the 3/5, and that's 0.66. So it says that the volume at point B is actually 0.660 cubic meters. Okay. So I hope this is okay, right? This is stuff you learn in algebra. It's kind of standard stuff you learn in algebra. It doesn't get used as commonly. So I completely understand if it takes a little practice to get back and remember how these powers work. But once you do that, this super adiabat formula lets you relate the pressures, the volumes, and the temperature ratios. As long as you have one of those ratios, you can solve for the other information. It is the approach that we're using here. So we're getting everything filled in. Ooh, there's more. So again, that adiabat, Q is equal to 0. The internal energy difference, the change in internal energy, the increase or decrease, is 3/2 nR delta T. It always is for a monatomic gas. Now, we knew how many moles there were. We calculated that up front. We know what big R is. What we needed were the temperature differences, and now we have it. So we know what the increase in temperature was. Delta T is 96 kelvins, and the delta E is going to be proportional to the delta T. The amount that the internal energy goes up is proportional to how much the temperature goes up, and that worked out to be 48,000 joules. Now, how does that divide up between Q and W? Well, it's an adiabat. Q is 0. So it says all of this energy is coming in due to the compression. So work is bringing in 48,000 joules. I didn't put the minus sign here. I used the diagram. So nothing is happening on the Q side. The internal energy goes up by 48,000 joules, and that says that's all coming in from work through the compression. By compressing the gas, we are transferring energy in through work. Now let's move on to the next process. This was an isotherm. Now an isotherm means that the temperature at C is the same as the temperature at B. That's still at 396 Kelvin. And what that says is, hey, the internal energy is not going up anymore. The internal energy is going to stay fixed along this path. Now what I did was I used that ratio trick. I wrote down PV equals nRT for point C, and then I wrote down PV equals nRT for point B, crossed out the ends, the number of moles stays constant, big R is a constant, and it's an isotherm, so the temperatures are the same. So I can cross out anything that's identical. And that says that this ratio then is 1. So solving for PC, it's pressure B, VB over VC, putting all the numbers in, it tells me that at point C, we're going to be at 264 kilopascals. So we're going to go from 100 kilopascals to 200 kilopascals to 264. And let's take a look at the, there it is. So this was the drawing they gave us. Point A was at 100 kilopascals, B is at 200, and now we know, using the isothermal formulas, that point C is at 264 kilopascals. All right. Now on this side, the work we can calculate for the isotherm. We've derived this formula earlier. This is going to be 36,000. Now this is still work going in. I did put a minus sign here. I need to stay consistent, I guess. In both steps, energy went in through work, 48,000 joules in that step from A to B, and from B to C, 36,000 additional joules went in. So that says it all. So, but in the, it doesn't quite say it all. So in the isothermal case, the compression brings in 36,000 joules, but then we lose the 36,000 joules due to heat loss. So whatever energy came in through work is lost through heat. All right. Now let's move on. We've looked at these thermodynamic processes. Let's take a look at some ways that heat can be transferred. Now we usually think of heat transfer as happening through either conduction, convection, or radiation. And the picture we have here is for heat conduction. So I've got a region where the temperature is hotter, and it's in thermal contact with a colder region, and just from random molecular interactions, the trend is for the cooler region to acquire more kinetic energy and the hotter region to lose kinetic energy. So there are what are called thermal conductivity properties for different materials. So we got all these materials listed, and then we have the thermal conductivity, and to represent the thermal conductivity, oh no, we're using a symbol little k. How did that happen? We've used little k for everything, right? Little k was supposed to be Boltzmann's constant, but now we're using it for thermal conductivity of a material. Now if we go back and look at the formula here, it says that delta Q delta T, which is the rate at which energy heat will conduct through a material, depends on its thermal conduction times the cross-sectional area that the heat has to work with, times the temperature difference divided by L. So let's look at an example of using this. So here is a window. So let's say we have a house or a building of some sort, and we have a window, and the window has a thickness of, the window's only 3.2 millimeters thick. Is that thick enough? Maybe. It seems like a thin window pane. Don't run into it. I think it's going to break. This seems a little bit thin to me. The window's pretty big. It's got a cross-sectional area of 3 square meters. It's a good sized window. I like that in a house. And then the temperature outside is 14 Celsius. Now what they're saying is the temperature inside is 15 Celsius. That sounds cold to be inside, but the reason we're using 15 is because if you're inside a house with a single pane of glass, the temperature near the window is going to be pretty low, right? You can walk over on a cold day, of which we have none in the Bay Area. So this applies much better for a more extreme environment. You know, you go somewhere where in the winter it really freezes, and in the summer it's like, 100 Fahrenheit outside. So in this case, it's pretty chilly outside. 14's not that terribly cold, but 14 outside. Inside it's probably 25 in the room, but near the windows it's at 15. So anyway, they're thinking in terms of not such a large temperature difference. So let's plug it in. So the energy rate, the rate at which energy is transferring through that window, is the thermal conductivity of glass, and that works out to be 0.84 joules per second, meters per square meter. If you check all the units, that it has to cancel all the units correctly. The temperature difference is just 1 Celsius, and the cross-sectional area is big, that's 3 square meters, and then the thickness was 3.2 millimeters. I put that in meters. I plugged everything in the formula, and look, what it's telling me is I am losing 788 watts, or I'm losing 788 joules every second. That's a lot. That says to compensate for just this one window, I need to get a heating system inside that can provide 788 watts of heat. I got to be generating that. That's a pretty good sized space heater to provide that for just the one window. For every window, we'd have to add to that. So you can see the importance of double pane windows with maybe an inert gas in between to minimize those losses. Now, in addition to conduction as a way that heat gets transferred, there's a process called convection. So here we are, we're heating some water, and the water is heating up at the bottom, especially a lot in the middle, and as a result, that water is at a higher temperature, it's not as dense, and so it begins to rise, and the cooler water from the sides flows down. So that's a situation where the water is heated just at one location, but rather than waiting for conduction to happen, the water actually is naturally setting itself into a convection. And so this convection is going to help mix the water so that the heat that comes in ends up being transferred throughout the entire sample. Now that's natural convection that gets set up, and that happens in many cases. Here is forced convection. We got a furnace heating up a bunch of water so that it's really hot, and then pumping the hot water. So that hot water carries the thermal energy with it, and then it goes through some radiators and transfers the thermal energy into the rooms of the house, and then it comes back. So conduction, convection. The last item we're going to look at is heat transfer through what we call radiation. Now radiation means that the heat's being transferred through light. It's not necessarily visible light, it could be infrared, for example. But in any case, for this, this is like saying energy transfer from the sun, right? Clearly conduction is not going to be bringing energy, heat energy from the sun, or convection, there's really nothing for it to conduct or convect through. But what does happen is at any temperature, it turns out at whatever temperature an object's at, it is radiating photons. So everything around us, all objects, are radiating and absorbing photons all the time. Now, some of that could be visible light, but for everyday temperatures, 300 Kelvin, most of that energy exchange radiatively is through infrared. And you guys have seen infrared goggles, right? So you put on the infrared goggles, and you can see objects based on what their temperature is, and that's due to this radiative effect. Now, the radiative effect is proportional to temperature to the fourth power. Now, we don't see formulas like that have the fourth power in them very often. So the temperature makes a big difference. If you double the temperature, the energy transfer goes up by a factor of 16. Okay, so you're radiating 16 times as much energy if the temperature doubles. Then there's a factor of Stefan-Boltzmann constant, which adjusts all the units. There's the area of the surface. And then there's this emissivity factor that says an object, if it's really shiny, does not absorb or transfer or radiate energy very well. And if the emissivity is 1, then it's totally absorbing and totally radiative. So the emissivity factor applies for absorbing light or radiating light, both. And so an object that's very good at absorbing is very good at radiating, and vice versa. All right, the Stefan-Boltzmann constant has the value 5.67 10 to the minus 8 watts per square meter per Kelvin to the fourth. I don't think they got an order of operation right here. That needs to be in parentheses. You can't divide and then multiply. The kelvins are in the denominator. So let's look at a couple of examples. First of all, it says, let's imagine an athlete sitting unclothed in a locker room with walls. Now, when you're in a room, you're going to get radiative exchange with the walls. And so if the room is at a higher temperature, if the walls have been brought up to a higher temperature, the room will feel warm. If the walls have not been heated, let's say you've been away on vacation, the room got really cold, the walls and ceiling and floor are really cold, and you come back and you turn the furnace on. Well, the furnace starts sending out air that's warmer, but the walls take a while to heat up. And so the walls are not providing radiative heat, and the room will continue to feel cold, even if the air feels warm. So, so we can calculate at what rate is this person radiating energy, at what rate are they bringing energy back in, and we just use that formula twice. So here's the rate of the energy going away from the person. They said this person has an emissivity of 0.75, so they're pretty good at absorbing light and they're pretty good at radiating light. This is, again, going to be infrared, pretty much, at these temperatures. There's the Stefan Boltzmann constant. It says that the surface area of the person that's exposed, where the radiation could take place, 1.5 square meters, and then the person's temperature is 307. So that says that the person is radiating 529 joules every second. So you can see these radiative losses can be pretty significant. If you're in a room that's really, where the walls and ceilings and floor are all really cold, you're not getting much energy back, and you're losing this 529. Now, they said that this room is at 288, so it is a cold room. It's at 288 Kelvin. Wow. Why aren't they heating the locker room? Okay, it's at 15 Celsius. That's not too bad. 15 Celsius. It's a cool room. So the person is losing 529. When we calculate the radiation coming in, that is absorption. So the emissivity is the same as it was for radiation. Same Stefan Boltzmann constant, same surface area. But now the energy that's coming in is at a temperature representing the temperature of the environment that is sending the energy back. So energy is being radiated based on the person's temperature. Radiation is coming in based on the environmental temperature. And that's only 410 watts. So this person, if they just stay in that room, will continue to lose 119 joules every second from sitting in a cold room. And you're going to have to depend on the person's metabolic processes to provide the extra heat to make sure their body temperature doesn't begin to drop in that cool room. All right, there's a lot of stuff in Chapter 19. I know we've gone fast. If you guys have any questions, stop by office hours. We can certainly look at these. We do have one more example left, and that is looking at the giant star Betelgeuse, which radiates energy. Its power output, what we call its luminosity, is 10,000 times greater than the sun. It's 10,000 times the power or luminosity of the sun. Now, its surface temperature is actually much lower. It's only 1/2 of the surface temperature of the sun. What's going on? So let's take a look and see how we can address this paradox. So here's the sun. Now, I drew Betelgeuse as really, really large because it's referred to as a red giant. Now, what does it mean to be a star that's a red giant? Now, the power or the luminosity of the star is based on the rate at which nuclear fusion processes are happening. So the fact that Betelgeuse is 10,000 times as luminous, it radiates 10,000 times the power, means that its fusion reactions are 10,000 times as intense. So it's running nuclear fusion reactions at 10,000 times the rate of the sun. So clearly, it's a really luminous, high-power star. So let's get that cleared up. Now the sun has a surface temperature of 5,800 Kelvin. It's kind of in the yellow part of the spectrum. And Betelgeuse has a surface temperature of 2,900 kelvins, and the surface is red. Now the light we see from a star is coming from kind of the very outer layers, the outer 100 kilometers or so. Any light that gets generated by inner layers doesn't make it all the way out. It runs into some other gas molecules on the way out. And that's a good thing. In the core of the star, like the sun, the temperature could be 10 or 20 million Kelvin. These surface temperatures are nowhere near the energies at the core. Now at 10 or 20 million kelvins, the sun at the core is generating a lot of gamma ray energy photons and X-ray energy photons, and those would be very unhealthy if that's what it were radiating out into the solar system and that's what's being picked up on Earth. But as the light gets absorbed and then radiated and then absorbed and other light gets radiated, kind of this relay process, by the time they get to the surface, the light we see is coming from a 5,800 Kelvin object. So what we can do is we can do a ratio of powers and say that the power generated by Betelgeuse compared with the ratio of power from the sun is based on the emissivity, which we can set equal to 1 for both, times the Stefan-Boltzmann constant, which cancels out. Now this is the surface area where the light's coming off the surface. And that's going to be on the outer surface pretty much, on the outer layer. And that is going to be a surface area of 4 pi r squared. Now that's the radius of the star itself. So the 4 pi's cancel, but we have a ratio of the two different radiuses that remain, and then the temperatures. So we can take that ratio equation, solve it for the radius of Betelgeuse is equal to the radius of the sun times the ratio of the luminosity square rooted. Now that was 10,000 to the 1/2. And then the temperature is squared. And the temperatures are going to be, that ratio is going to be a factor of 2 squared. It says that Betelgeuse has a diameter, a radius or a diameter. It's 400 times the diameter of the sun. So what has happened with Betelgeuse is it's in a later stage of its stellar development. And what happens is the fusion kicks over to different fusion reactions. The fusion becomes really intense. And the outer layers get pushed outwards. So the size of Betelgeuse, we can calculate this using the, oh, I didn't put in the radius of the sun. That was in the original problem, right? There it is, radius of the sun. So I used that, plugged that in, and it says that Betelgeuse extends out to a radius of 2.8 times 10 to the 11 meters. That puts it out beyond the orbit of Earth. If Betelgeuse were placed in our solar system, it would be bigger than the orbital distance out to Earth. It would extend out beyond Mars. So that's a really big star. Now remember, it's really thin. The material that star is made out of is really thin because it's so spread out. But it has 4 times the diameter of the sun, and that becomes 64 million times the velocity. So that takes us out to the end of chapter 19. Again, a lot of stuff. Thank you for your patience with this. And I think we'll go ahead and, well, let's say just a couple more things here, I guess. And that is, in the future, maybe 4 or 5 billion years from now, we're expecting that the sun will also go through this transformation. Now, the sun's not as big as Betelgeuse. It's not made out of as much stuff, but it still will go through a red giant stage. Not as big as Betelgeuse, but what we expect by looking around the local region of stars and understanding how stars behave, what we expect is that the outer layers of the sun will also expand. And you guys have probably heard these stories, but that's based on our understanding of how stars develop and go through different stages of nuclear fusion. We're expecting that the sun, it's not going to reach out to Mars, but it would probably reach out to Earth's orbit, roughly. And so I think that would be so cool to be living in the future, 4 or 5 billion years from now, and watch the sun go through that transformation. So what would happen is, day by day, well, this would be over millions of years, I guess, but the sun would be bigger in the sky as time went on. Every day the sun comes up, it's a little bigger than it was before. Now, the surface temperature is going to drop. So rather than being a yellow star, it's going to start being more orange, and then it expands more, it gets bigger in the sky, and then it becomes more reddish, and it continues to get bigger and bigger in the sky. And at some point, it's so large, it fills the whole sky, and then it extends past Earth. So that would be so cool to watch, right? If you had a good, safe place to watch this from. Anyway, that's that's the kind of stuff that we understand happens during stellar development, what we call stellar evolution, but it's really the different stages of fusion that stars go through. All right, once again, thank you for your patience. We've gone through a lot of stuff here in Chapter 19. Whatever questions you've got, stop by office hours, and we'll get those questions answered. We'll get those looked at.